Okay. Morning all. It's a very momentous day here at Brookhaven. I'm really happy to welcome you all. Seeing lots of familiar faces here. Thank you all for coming. When I pause to think about why we're here to turn off the Relativistic Heavy Ion Collider and all that's done over the last 25 years. It's really humbling to think about that and what it's achieved. For 25 years, it's been accelerating atomic nuclei to almost the speed of light. Incredibly difficult thing to do, and then smashing them into each other to see what happens. We've had incredible detectors that we built over the years, the data that we then analyzed to understand exactly what the early universe was like. Just an amazing achievement if you think about it. The creativity it required, the precision it requires, the dedication it requires, the expertise from so many people. It's really extraordinary. Our key partner in this has been the Department of Energy throughout the years. I'd like to welcome Undersecretary Dario Gil today. Thank him for his support. Thank you for joining us. I want to thank our staff, the lab as a whole, who've made this machine run so well over the years, and the community that supported us in doing that. It's also a pleasure to welcome Linda Horton, head of the Office of Science Nuclear Physics Program and Deputy for the Office of Science. Paul Mantica, I saw Paul earlier, Director of Facilities and Project Management of the Division of Office of Nuclear Physics, and we'll mention Kevin Law later. It's a pleasure to be with you all, those in person, those online watching and around the world today. RHIC has produced trillions of collisions over the years, hundreds of petabytes of data. It's enabled more than 650 publications. 640 scientists have got their PhDs using this. I'm seeing many of them in the room today. And with all that output, RHIC has changed our understanding of the universe. RHIC recreated the quark-gluon plasma, the state of the universe a few microseconds after the Big Bang, and discovered that it wasn't a gas as had been predicted, but was in fact a near-perfect fluid. It helped reveal how the gluons contribute to the proton spin, and it also enabled some of our other programs here, the R&D in terms of radioisotopes, that has been so productive, and the NASA Space Radiation Lab. As a side, it's also been one of the highlights for the Summer Sundays that we run. Thousands of visitors every year come through, excited by the science we're doing and the scale of the science we're doing, and just to see it in person has been really inspirational and motivational to the public. Its success has required tremendous collaboration from the Department of Energy, from Congress, from the scientific community, from the local community. Thousands and thousands of people have been involved in the years in making this machine the productive machine it has been. And I want to thank you all for that contribution. Scientists, engineers, technicians, operations staff, all have been required to make it work as well as it has done over the years. I also want to thank all the members of the RHIC collaborations over the years, Phobos, Brahms, Phoenix, STAR, and S-Phoenix. Thank you to all the members of the RHIC BNL Research Center, which has been so helpful in making this thing work, and everyone who's designed, built, and come into contact with the machine over the years. I joined Brookhaven in 1992 as a material scientist. I was director of Light Source 2. I took part in the moment when we turned Light Source 1 off and started to think about Light Source 2. This is another such generational change. They don't happen often, every few decades. And I know this is sort of a bittersweet moment. The loss of RHIC, which we've been such a productive machine that we've been so part of all these years, and the excitement of the new machine and all the science it's going to do. So both motions I think we're all feeling today. When RHIC was built, it leveraged the accelerators that we'd already had here at Brookhaven, including the AGS, which was the home for 3 of our 7 Nobel Prizes. And as RHIC concludes, we're going to again reuse these assets for the next machine, this time to build the Electron-Ion Collider. The EIC is going to answer some really important questions about the structure of matter. What is it that makes us up? The origins of mass and the mystery of spin. Really fundamental questions of science that we'll be able to answer here at Brookhaven. The EIC is going to be built in partnership with Thomas Jefferson Lab. I see David Dean here from JLab, with the DOE, with New York State, and our collaborators worldwide. It's going to be the only machine of its kind. It's going to leverage the discoveries of RHIC to move into this new phase of collisions. It's going to leverage AI from the moment of its design through construction and operations, through discovery. And so much of it, EIC's future success will be built on what we've done here at RHIC to date. But now RHIC is over. Its operation is complete. The science will continue, but today marks the end of data collection. We're here to celebrate that success story. All the brilliant scientists, engineers, technicians, and support staff, partners from around the world, our policymakers who've advocated for RHIC and supported it through the years. Many will continue their roles as we move forward now into EIC and the excitement of what comes next, and so I'm thanking you all for your parts in that. It's now my honor to call upon Dario Gil, Undersecretary of Science. We know Dario well for many years as Director of Research at IBM. Today he heads the US Department of Energy's Office of Science and DOE's Genesis mission. Dario, I'm going to like to ask you to have the honor of pushing the button that's going to close RHIC. The button is over here, big red button. And we're gonna count down before you hit it.
Okay.
So
I will not jump the queue.
just explain what you can see on the screen. So these are the detectors running right now, and so these traces are the collisions that are happening right now. There's a little bit of lag as they analyze the data before we see them, so they may not disappear the instant you hit the button.
Yeah.
But the instant you hit the button, the machine is going to go off. And if you look at these traces over here, they will disappear at that moment. At least I've been promised that's what's going to happen. Here's the big red button. Think maybe count down from 5?
All right.
5, 4, 3, 2, 1. The traces of. There we go.
Oh.
And the collisions have stopped.
Whew. Congratulations. Thank you. All right, thank you. That's right.
Would you like to say a few words?
Yes, please. Thank you. Well, thank you all for being here today, and for those in the room, and for everyone watching across the country and around the world. Today we're doing something rare in science. We are closing one of the most successful research facilities ever built by the US Department of Energy. At DOE, we build facilities meant to last decades, and that are continuously retooled and advanced as technology and scientific questions evolve. We measure success not just by how long they run, but by how profoundly they change our understanding of the world and enable discovery at the frontiers of science. By that measure, RHIC has been an extraordinary success. RHIC represents what the DOE Office of Science and its national labs exist to do: to take on scientific questions that are too complex, too ambitious, and too long-term for any single institution or nation, to build one-of-a-kind tools to answer them, and make those tools available to the national and global scientific communities. Since first collisions in 2000, RHIC has produced nearly 300 trillion particle collisions. It has supported thousands of scientists from more than 30 countries and led to hundreds of scientific publications that reshape the field of nuclear physics. RHIC provided exactly what we hope from DOE facilities. It far exceeded its design performance, went beyond its original mission, and delivered exciting new science year after year. What scientists discover here surprised the world and transformed our understanding of the strongest force in nature, the building blocks of visible matter, and fundamental quantum properties like proton spin. Today, those insights are embedded in the foundation of modern physics textbooks, and they all began here at a DOE national laboratory. RHIC has driven breakthroughs in science and propelled advances in technology. Thanks to RHIC and the people who worked on it, we pushed the frontiers of accelerator performance, particle detectors, high-performance computing, and large-scale data management. The final run alone generated hundreds of petabytes of data, including the largest data set in RHIC's history, more data than all previous RHIC runs combined. Equally important, RHIC trained a generation, more than 600 PhDs alongside engineers, technicians, and operators whose experience now strengthens the US scientific workforce across a wide variety of disciplines. This is the long-term national return that DOE investments are meant to deliver. RHIC operations are ending today, but RHIC's scientific impact is far from over. The data collected here will be analyzed for years, perhaps decades to come. RHIC's results will continue to inform experiments around the world. And critically, RHIC's infrastructure and workforce will form the backbone of what comes next, the Electron-Ion Collider. At the Department of Energy, stewardship is a core responsibility. That means knowing when to begin and when to conclude a great scientific endeavor. RHIC operations end today because the machine has fulfilled and exceeded its mission. I want to thank the scientists, the engineers, the technicians, the operators, and staff who have made RHIC one of the most successful user facilities in our history. RHIC showed us how matter behaved at the dawn of the universe, and it paved the way for the next generation of discovery. It is a great honor to mark this moment with all of you. Thank you.
Thank you, Dario. We're very grateful you could be here today to mark this milestone with us. I'd now like to invite Abhay Deshpande to give some remarks on the RHIC mission and the EIC mission. Abhay is Brookhaven's Associate Lab Director for Nuclear Particle Physics. He is also a distinguished professor at the Stony Brook University. Abhay?
Thank you. So between John and Undersecretary Dario, you have covered my talk. But I want to give you one step deeper. I think it is really important to realize what the impact is of RHIC and the future. So let me start. It has been a very successful partnership, particularly with Japan. RHIC BNL Center is a really important part of the RHIC's initial beginnings and also later. To mark this opinion, the president of RHIC has sent a message, so let me play that for you first.
Distinguished guests, colleagues, and friends, on behalf of RHIC and the Japanese science community, I would like to express our deep thanks to the U.S. Department of Energy and Brookhaven National Laboratory. For RHIC, working in this great international environment has been a truly valuable experience. We are very proud of the strong trust we have built together. Our journey started in the early 1990s. Through Phoenix, STAR, and the SPIN program, our partnership has grown step by step. Together, we have learned important lessons about quarks, gluons, and the spin of the nucleon. These results have greatly improved our understanding of the nuclear matter. At the heart of this collaboration is the RHIC BNL Research Center, RBRC. It is not only a research center, but also a place to train young scientists from around the world. Now, as we move toward the Electron-Ion Collider, this partnership enters a new stage. By connecting low-energy and high-energy nuclear physics, we are opening a new way to study quantum dynamics across many scales. This will help us better understand matter and the origin of the universe. The end of the RHIC program is not the end of our story. Rather, it is a new starting point. RHIC will always remain a symbol of trust and friendship between the United States and Japan. We look forward to walking into the new scientific frontier together with our dear colleagues and friends. Thank you to everyone who made this history possible.
So the partnership that he mentioned that created lots of supported young scientists here at the beginning has continued over 25 years. I'm a living proof of that. I was one of the early scientists who came here as an advanced postdoc in year 2000 to work on RHIC science. So they've created 70 plus positions around the world in the US, Japan, and in Europe that have now worked on RHIC for the last 25 years. So this is really a very impactful partnership that we have benefited from. Having said that, let's go to the celebration on RHIC and preparing for the EIC. We're going to celebrate 2 milestones here. One is the smashing success that the Relativistic Heavy Ion Collider has been, with the 25 years of operations, world-class operations, groundbreaking discoveries, and sustained scientific output that will continue into the next decade. And at the same time, the beginning of the Electron-Ion Collider, which also provides transformative physics research opportunities, advanced accelerator and detector computing technologies, and of course, built into the fabric of it is the AI at all levels, and that's what we should be coming through. And most importantly, we are also here celebrating all the people, the scientists, the engineers, the technicians, the support staff, that was so critical for the 25 years of success here. From Brookhaven National Lab, from other DOE labs with partnerships across the US and around the world. The support from, of course, DOE and Congress in New York State is absolutely critical for that success, and we hope that that continues into the future in the EIC era. So studying nuclear physics is a journey into the early universe. You look at the beginnings of the universe, we want to know what was the condition of the universe just after the Big Bang. We are looking for things a microsecond after the Big Bang, where quarks and gluons were still free and protons, neutrons were not formed. What was the condition of the universe at that time is something that we would like to know. At the same time, there's a transition from those quarks, gluons coming together to form protons and neutrons, and then eventually evolve into everything that we see today. That's also a transition which we are very curious about, and only accelerators allow us to do that. And this is why we are here in the left side, where you see this first disk. That's the region in time that we are exploring this transition from. It turns out that that also allows us to look at the most fundamental. What is nature made up of? Those are the questions that we are all curious about, and that's something that these colliders allow us to do. When you get multiple quarks together, how do they know how to form a proton with the exact quantum number that we know? That's something that we want to understand in all aspects. As was mentioned, the mass and the spin and how they interact within each other to form the nucleus. All of that is a question that we want to answer. So let's start with the Relativistic Heavy Ion Collider. It was a machine to explore fundamental matter at the dawn of time. What you see in this picture here on the left-hand side is a large injector complex which injects the beam. You can see the smaller rings, the AGS, and those are accelerator components that put the particles to higher and higher energy as we go through. And then eventually they come to the RHIC, which is on the top here. And in the RHIC, we accelerate this nuclei to light speed. And you put them in 2 counter-rotating beams, and they start accelerating. They go to the top speed, and then they collide at a few different places where there are experimental areas. Once they collide, what you see on the right-hand side are pictures of the events. You see how dense, in terms of number of particles, the event looks like on the right top. That's an actual distribution of particles that came out of a star collider detector. On the bottom is a similar one, a picture taken by the S-Phoenix collaboration here, and you will visit that today and learn how they operate. Over the time, there have been many multiple experiments that have run over different times, and those are listed there. And if you're going inside the tunnel, you will see this picture right here, how the tunnel looks like, these two beams. So RHIC has been an outstanding success, also because it has been a very versatile detector, collider, with not just the high intensity and the brightness of the beams, but it has run at 49 different combinations of energy, species, and collision configurations. There is no collider in the world which has ever done that or even planned to do that in the future. There are 10 different ion species, center of mass energies, and the innovative accelerator technologies that had to be invented to make all this happen has allowed us to exceed all the initial design parameters. It still remains the only collider in the world where the proton spin can be controlled in the entire tunnel and then manipulated when you collide. That is a really important thing, that what you mentioned about the nucleon spin, the proton spin problem. That's the only place in the world you can do this research. So what happens in a quark-gluon plasma research? So you saw that there were two large nuclei that came in with neutrons and protons. The quarks are inside, confined at that time. But because of the large energy collision, this gets built, they basically melt. And what you see is, for a fraction of a second, the quark-gluon plasma is formed. It, of course, starts cooling down quickly, and particles are created, which are then captured by the experiments, and then they have to decipher what must have happened in that high-energy collision. So that's the method that all the experiments use, and this is where the modern techniques will help tremendously in terms of getting to the answers fast. So on the right-hand side, you see the phase diagram. On the x-axis is the density of material. On the y-axis is the temperature. You normally expect that you increase the temperature, things start melting from solid to liquid, liquid to gas. What we saw in the quark-gluon plasma, we expected to see a gas, but it turns out it flowed like liquid. It was a very surprising thing. With a very low viscosity, almost near the quantum limit. The temperatures measured were about 4 trillion degrees centigrade, the hottest matter ever created at the time when we were starting to do this 20 years ago. It's a unique transition from gas to liquid when you heat the system. You think about that. You heat the system, and then it sort of reverses the direction in which you expect. The density that we measured was extremely high. So these high-energy particles that try to normally come out of the collision, they are completely quenched, and you'll see in the cartoon there, it's very asymmetric. You see one jet come out, and there is nothing at the back. And that tells us how dense this material that we are creating should be, and that's astonishing in terms of that density. I mentioned to you the proton, the only polarized proton. So what happens is that these protons are polarized, they're put into the collider, we maintain the polarization all through the top energy, and then we collide them in the experimental area with our controlled spin orientation. Coming into the program, we knew that the quarks that are in there carry about 25% of the proton spin. We thought it was going to be the rest of it was going to be gluons participating in that process. We didn't know what exactly was going to be. There were some ideas about it. Over the 20 years, we've measured it now. It turns out that the gluons carry almost the same amount of proton spin. So that's what he showed on the yellow part there. This creates a next mystery as to where is the remaining quark spin coming from? And that's the question that the future Electron-Ion Collider is going to solve, not only make those measurements very precise, but possibly try to understand the dynamic nature of the spin that comes in, or the quarks moving in there, to see if we can get to that last open question. This has been a tremendous success, 300 trillion collisions, 450 petabytes of data, 650 publications from people who have participated from 36 countries and about 650 PhD theses. So this is something that is really, really important. And the productivity scientific continues. You see the two most recent papers published this week. One using the AI to decipher the event structure. You will meet people who actually did that in the next part. And they're also going into quantum vacuum studies, which was also not part of the early part. New things that have come up just because of the innovative nature of people who have worked and decided. So now we come to a bittersweet day. We just closed off last collision, and we're going to transform this wonderful collider into a new one with a bright future again for the next 25 to 30 years. We are going to use $2+ billion of investment from DOE to use it again for the future. That's no small thing. What we're trying to do is to get one of the rings out of the collision. So one of the hadrons will come out, and we'll put an electron beam facility in there, which is shown on the right-hand side. And at that point, we'll do collisions with the electrons with the remaining hadron ring with some modifications. AI, as I mentioned to you, is inbuilt into all aspects of it, from accelerator operations and optimization, data acquisition and detector electronics, to data analysis, and also to understand what that data means to interpret in terms of the final physics products. So what is the difference? Why are we doing this? So here is a cartoon that shows you, I showed you the quark-gluon plasma that exists for some time. That's like colliding two watermelons and trying to see what happens when they are. But now we have to be more precise and understand, how does the transition of the quarks to gluons to the protons happen? How do they come together when they're bound? And that's like the electron being a knife instead of two, probing with two watermelons. We are hitting one watermelon with a knife. So you can cut it and in a controlled way with a precision, so you can understand the internal structure much, much better. And then you can do that with the nuclei and everything that we want to study. So that's the difference of EIC, brings immense precision and control over what you want to see inside. So the picture of the proton in 1975, when I was in high school, was of this kind, that it was made up of 3 quarks bound by these gluons. But now we know that it is evolving. There's a lot more going on with the gluons, a lot more might be going on with the motion, and that's the picture that we will eventually create, not just of the proton, but also of the nucleus going forward. So the 3 main pillars of the EIC science, as was alluded to, understanding mass. If you just add up the mass of the quarks and gluons, it can explain 1 or 2% of the total mass of the proton. Where is the 98% of the mass coming from? And that comes from the gluon-quark interaction. The energy of that creates the E is equal to mc squared transition, and somehow that comes about. But that's something that we would like to understand. The same dynamics is also going to create the spin of the proton. The remaining part that I mentioned to you, that's another thing. And last but not the least, the gluons have a tendency to interact with each other, which is a unique property only the gluons have, only the strong interactions have, which means that the gluons can keep on multiplying inside the proton or the nucleus. And that's something that we want to understand. It seems to create a purely gluonic form of matter with tremendous properties which we can't even imagine. Just mathematically we can estimate. And that's something that we want to see if that really happens and really deeply understand the role of gluons in entire things that go on. Of course, it will not only significantly enhance our knowledge of fundamental science, but it will be helpful for health, medicine, accelerators, in industry, AI, computational tools, energy and national security, and also, importantly, workforce development that can go out of the science and go into the society. Of course, the science is so critical, and people around the world understand this is the only place to solve these problems. There's no other collider even comes close to solve these problems, and that is reflected in this plot. You will see people from 41 countries have already committed to coming here to work with us 10 years from now. So this is something that reflects the excitement of the people around the world. There's also Brookhaven and Jefferson Lab, our principal partners, but all other 8 national labs are also part of this, are there. There are user groups, has about 1,500 people around the world from 41 countries, as I mentioned to you. The time of EIC has come now. You just shut down a large, very, very successful facility, and now we are looking forward to going to the next phase and use all of that, the knowledge and everything that we have built over the last 25 years and more into this future. It will actually have transformative discoveries. It will keep US on the forefront of nuclear and accelerator physics. There will be advanced technology, of course. Significant investments and commitments are coming from international partners. And last but not the least, we are using the infrastructure as best as we can so that the taxpayers get the maximum out of this. And this is it. We have the people who will make EIC happen, because the expertise that we have built over years, collaborations that we have built years, the people who guided the early part have taught that what is needed for the next generation, and you're going to see some of the next generation soon to go into the EIC in the future. So we want to thank the workforce at Brookhaven, across the DOE complex, our partners, at other national laboratories, collaborators, universities around the world. And of course, this cannot happen without the support from the DOE, Office of Nuclear Science. It's really, really important, and the Congress and the state of New York. Thank you very much. And now I'm going to introduce a young person who is going to really build this and actually use this collider. So come here. You're green, right?
Yes.
Yes. You have slides? Or?
I don't.
Okay, then you don't need it.
Good morning, everybody. My name is Jonathan Green. I'm a mechanical engineer, and I work on the Electron-Ion Collider. Some of the things I do in my day-to-day include designing pressure vessels, cryogenic cooling circuits, and support structures for what are known as the triplet magnets. They're a set of magnets that focus the beam right before the collision point and help produce collisions. One of my favorite parts about working at BNL has to be the fact that I get to see my designs all the way from concept through installation, and that's not something that you normally get to do as a mechanical engineer. In my day-to-day lately, I've been using AI to help me sift through some safety codes to make my designs more safe and compliant, and I'm really excited to be working on this project.
Hi, good morning. My name is Thea Vijayakumar. I'm a mechanical cooling systems engineer within the infrastructure division of the EIC project, and my role and responsibility day to day is to design all of the cooling systems for the future Electron-Ion Collider. So that includes all of the thousands of components of magnets and vacuum systems in the tunnel themselves, using the existing infrastructure like Abe had mentioned, as well as in the new service buildings that we are constructing in the infrastructure division. And prior to joining, I was a DOE SULI intern, so I learned about EIC through that internship, and all of the work that they were doing really made me inspired to join the lab full time, and I'm really excited to see what comes out of this, and I work very closely with all of the scientists and engineers for this new EIC project, so this is an exciting opportunity for me, and I could see it from start to finish. Thank you.
Good morning, everyone. I'm Andrei Natochi, and I'm research staff here at BNL. And I work on protecting both the collider and detector from effects of high energy and high intensity beams. I bring experiences from world's leading colliders, and I apply this knowledge here at the EIC. Looking ahead, I'm exploring AI and machine learning to improve safety and operational stability. And I'm excited to be a part of these pioneering efforts to make the next generation collider physics safe, innovative, and world-class. Thank you.
Good morning. My name is Jennifer Masico, and I'm a senior piping designer and mechanical engineer here at the lab. I serve as the link between the EIC cryogenic engineers and technicians, translating their designs from reality into reality by creating models and piping routes and cryogenic equipment. Right now, I'm working on the SRF cavities over at the AGS testing facility, where we will be testing the cryo modules that we receive from JLab before they are installed inside the EIC tunnel. I am also working on the modifications of the cryogenic piping throughout the tunnel at 3 of the interaction regions. I will first start off with a 2D floor plan. This way we can visualize equipment placement and potential piping routes. Once the design is finalized, I will create 3D models and collaborate with the technicians on the installation and fabrication, producing the final construction drawings. I am beyond excited to be working for such a groundbreaking project. Thank you.
Good morning. My name is Jonathan Bellon. I'm a mechanical engineer for the EIC vacuum group, and I work on designing the chambers which house the beam as it circulates in the ring. And today's an exciting day for our group because a lot of the RHIC vacuum components are going to be upgraded and repurposed for EIC. So with the conclusion of RHIC operations, we can begin testing and implementing those upgrades. Our group isn't just responsible, though, for RHIC upgrades. We're also responsible for over 3 miles of brand new ultra-high vacuum chambers. I've been with Brookhaven for 5 years, and it's never stopped being a joy to work on the practical engineering challenges that EIC requires.
I think that concludes our ceremonies this morning. I was looking around, I didn't see too many tears as we turned Rick off, but I saw a lot of excitement about EIC, so that was really fun to see. Thank you again, Dario, for your role this morning. Really appreciate that. Thank you all for coming. We're going to go off on a tour and see some of these hardware that we've just been hearing about. And enjoy the rest of your days. We're going to get together again at 11:20 in Berkner Hall for all hands meeting. Dario will be talking, and I hope to see you all there. Thanks very much again.